for joining our workshop. And I'm obliged to let you know that we will be recording the whole workshop. And with that, let me go to the slides. A warm welcome to everyone, especially from us, the organizers. I thank my colleagues. I thank this team for their tireless efforts in helping us to set up this very exciting workshop. Okay, so first and foremost, would like to thank our sponsors. We have three main sponsors, Draper Labs, Black Swan, as well as the Australian Space Agency. Thank you very much for your support, generous support. We have a number of affiliated organizations as well, as you can see in the bottom. And these are mainly the organizations that the organizers belong to. Okay, so for those of you who are unfamiliar with Zoom, this is where you find the chat functionality. This is the best way for you to interact with the organizers as well as everyone. Someone will be monitoring the chat window. So if you have any questions at all during the session, just type away in the chat window. This is our program for the whole workshop. As you know by now, at least maybe the presenters and speakers, our workshop is divided into two time blocks today. Well, currently we are in block A. So that's the program you see there. Just letting you know that at the end of today's session, at the end of today's block, we will be presenting 3 awards: a Best Paper Award, Best Paper Finalist Award, and a Best Presentation Award for Block A. Okay, so stay with us till the end of the session, please. All right, so for the authors who will be presenting, you'll be sharing your screen. Currently, you won't be able to do that because you haven't joined as a co-host. When we get into that session, all of you will be made co-hosts, and you will be able to share your screen as well as unmute yourself. For those who are unfamiliar with Zoom, this is the 2 buttons that you will need later to share your screen as well as unmute yourself. Okay, letting you know now, because we need to be super efficient here. Every spotlight paper is assigned 5 minutes. Okay, so also we will be interacting with you more actively in the poster session, and we'll be using the Gatherly tool here. Here is where you access that Gatherly. So the landing page for the workshop at CVPR virtual site. Okay, so if you haven't used Gatherly before, so welcome. This will be my first time as well, but we've tested it out and it looks kind of like this. We have 9 stalls, A to I. Take note for the authors who are presenting today what stall you're assigned to, and you can check this list again at the conference, at the workshop website. Okay, so when we go into the poster session, please stand virtually in front of your stall, your assigned stall. Okay, with that, let's begin the conference proper. All right, so Shirley's here. Okay, and she's made co-host. All right, gives me great pleasure to introduce our first invited speaker, Professor Shirley Ho. Shirley is the leader of Cosmology Cross Data Science Group at the Center for Computational Astrophysics at the Flatiron Institute. Her research interests range from fundamental cosmological measurements to exoplanet statistics to using machine learning to estimate how much dark matter is in the universe. I can tell you that for a CVPR audience, these are very, very exotic and interesting topics. Professor Ho is definitely an accomplished scientist. She has broad expertise in theory, observation, and data science. We are extremely honored that she can be here today to share with us her significant experience on machine learning for cosmology. Over to you, Shirley. I think now you can share screen as well as unmute yourself.
Yep. Thank you so much, Tetra, and thanks a lot for the invitation. And I'm very happy to be here with you guys today. I'm going to try to share a screen and see if it works. Seems like it's working. Yes. All right, I'll make it bigger. All right. So I don't know what Tadrian wants to do exactly with the questions, but I'm happy to be stopped in the middle, and I probably will stop in the middle and call for questions, and people should feel free to type, and I'll try to answer questions on Zoom as you type it in if you like. I'll be talking about something hopefully not too exotic for this crowd. It's called, okay, hold on a second. Yes. It's called Learning Symbolic Equation with Deep Learning. I'm Shirley Ho, as Tadrian just mentioned. I also have a joint appointment at NYU and visiting appointments at Carnegie Mellon and Princeton. I am sharing work with my students, Miles Kramer, and also a student from Princeton, Rui Su, also a student from Princeton, Pablo Lemos from University of Sussex, and now Jeffrey, also from ENS and IAP, actually. I just realized he just moved. And of course, with my very nice collaborators that I've been working a lot with, Peter Battaglia and Efraín Sanchez from DeepMind. Also, there is Spergo, who is currently still the director of Center for Computational Astrophysics and will be moving as the foundation president for Simon's Foundation, and Kyle Kramer from NYU. So I borrowed liberally the slides from my collaborator, Peter Battaglia, and I hope you guys will enjoy the talk today. And feel free to ask questions. I'll try to stop in the middle and answer questions as well. All right. Thank you so much. And without saying anything, all this work is very obviously done a lot, very heavily by the students in the postdoc. And so without them, we won't know very much what to do. Miles Kramer had written extensively on the Twitter, actually, and blog about this work too. So I'll be happy to share with you the link later on too. All right. So how do you understand a scene? So this is less astrophysics, more CVPR, I guess. If you look at a scene like this, and a lot of parents or people who have young kids in the house recently have seen this very often because the house is in chaos. And you very often ask yourself, what would happen next? And humans will parse it into physical objects and relations very easily. And we reason about the objects and their interactions. So when it's attached, this shelf of stuff is attached to these toy boxes, a toy is falling out too, a toy is hitting the guitar, the ground supporting the shelf and the guitar, for example. And we will call it precarious. So when you formulate that word in your head, you're already parsing out the situation and trying to figure out what will happen next. And it's surprising, but not too surprising. The linguists like to think about it as an intuitive physics engine. And this is something that I even learned from Pete, that if you look at a bunch of situations and one of them, say, a lot of blocks build up like this, you evolve forward from time t0 all the way to time t+1, all the way to time t+n. And you try to see whether it will fall and in which direction it will fall. And they've done a bunch of experiments. These experiments are very interesting because one of them is you show these simulations and ask the humans whether you think, say, for example, this tower will fall. And at the same time, you train the network, which has seen many, many of these things falling or not, and decide whether it will fall or not, which is kind of interesting, right? And it turns out the humans and the network surprisingly do very similarly. And in which direction it will fall is another version of this. And you can also do it with different masses that they're all completely different. And you can still see the network trained and the humans agreeing very often. And it's much more complex scenes here. For example, what will happen? How many blocks of red and yellow will fall off? There's also another predictions can be made by the humans and the machines. And sometimes you don't know what the masses of these blocks. So there's a hidden variable here that you can actually derive from the network. And fluids too. So you can see how much water is on each side, depending on this complex block situation, and also even how this one is set up. So all these things is a reasoning that we have in our head that humans can actually make a good, very good guess. And so is the machine when it's trained often enough. So scientists do the same thing. And here comes a more astrophysics version of things. If you see a bunch of planets moving around, say our sun, you can say that time t0, it moves forward like this. And for the next step, it will also move like a little bit more. So you have this step-by-step predictions that you can make. And by observing these systems, can we figure out what rules that govern them? So Isaac Newton, famously, supposedly, I don't know if that is true, has figured out that the fact that the apple falling on the ground is the same rule that actually govern how Earth goes around the sun. And this is a famous tree, supposedly, in his manner. This is all Wikipedia, so don't blame me if I got the wrong tree. But we did get the right law, and at least classical Newton's law. So we can go from here, observing a bunch of planets moving around, and get the physical laws. And very often, we want to do the same thing. So right now, I show you the network can make good predictions. Humans can make good predictions, but network also can make good predictions. And now I'm also showing you that we can take these predictions and hopefully parse it into a rule or empirical law. It can be an equation. And for the longest time, people always complain about machine learning when you can make good predictions is a black box. So how do you make this black box understandable somewhat? You can go for the explainable AI route, or you can go in the route as, can I take a prediction that this network has made, that is made by this network, and say, try to understand what the network is doing. And furthermore, understanding what the system is doing. So that's what we're going to talk about today. Traditional, what we're going to do, we'll observe the planets moving around. We try to figure out the physical law that governs the motion of the planets. We either work super hard or be really lucky, or both, and came up with it, like what Newton did. Or we're going to talk about something called symbolic regression today. It's related to genetic programming and evolutionary programming. It's long history. I don't pretend I know everything in that direction, but the idea of it, I will explain a little bit today. So what is symbolic regression? It is, we have a bunch of mathematical functions and variables. We form new equations, and then we check whether these new equations fit the variables, and then we move on to the next equation to find better fits. And depending on which algorithms you use, how you move on to the next equation and how you search that space will depend vastly on what you're doing with the search. So this is a very basically smart search with a very large space to search for the right equation. And today, what I'm going to try to do is that you can use a graphical neural network to help predict the dynamics first of the system. And then we're going to take a little chunk out of this graphical neural, the important chunks that we don't know what they are, and use symbolic regression to derive these laws. Okay, so this is our group's sort of first try to combine inductive biases, such as, what kind of network architecture you should be using, and how picking the right architecture actually can help you understand what the network has learned, because you can extract the symbolic forms out of it. You can imagine the same thing happening, for example, in molecular dynamics or protein interactions for things that are much more practical. But in our case, it's less practical, but it's very useful. Newton's law governs many things. So how we like to do this in 2 steps. We take a data set, could be a bunch of particles. We predict the dynamics using, for example, in this case, graphical neural net, which is nearly perfect for this data case. And when you train it, you have to encourage low dimensionality representation in the chunks that you don't know about. And you plucked out those chunks and fit it into the symbolic regression algorithm and try to find, for us in this case, a known spring law or a known Newton's law, or some unknown things, which we'll show later. So the cool ideas here to remember is, how do you take network that can make really good predictions and combine it with symbolic regression to extract equations we don't know about the actual system that the network has observed and can predict really well. All right, so that's what we're going to do today. But let's concentrate on the predicting dynamics part. And neural net is great with this. You guys all know this. It can make great predictions. Make predictions, compare weights. And why do we use graph network in this particular case? For those people who don't do graph network, I'm going to quickly introduce one type of graph neural net. There are many types out there. It's called interaction network. Graph is a very natural way to represent entities and their relations. Their nodes, their edges, and the nodes here correspond to entities and objects and events. So V1, V2, V3, these nodes here. And you have edges, these E1, E2 here, which can be directional or bidirectional or unidirectional. It corresponds to the relations, interactions, and transitions. And the inference about entities and relations really respect the graphical structure. The graphs can really capture many complex objects and relation systems. Can talk about molecules, I mentioned before, mass spring system. Interesting part here, the spring is represented by many nodes, and they interact with each other with these edges. The n-body system I showed earlier is a fully connected graph, which could be different masses, and each nodes have possibly different properties, right? Different masses, maybe different velocities. Rigid body system, the wall here can be represented as a node, for example. Can represent sentences and parse trees, and you can even look at a scene graph. For example, for those who, hopefully we are not still talking about the pandemic too much, but when the pandemic just happened, I started looking into using the neural network, graph neural network, to represent different cities for the nodes, and sort of like how much is going on from one city or one group of people or one counties affecting another counties in terms of new cases and rates, and use the data to model it. So it could be events, and it could be transition from one place to another. It could be positions. There are many things you can do with the GraphNet. Go into a little bit more details. You can look at this n-body system with a little bit, tiny bit more details, because we're going to look at it very carefully later on. We have the edges, we have the nodes, this is global variable. For those who are science inclined, you might have heard of these conserved quantities, like conservation of energy or angular momentum, or just simply masses. Or for those who are not so interested in science, you can think of, if there's a room of people with a lot of people coming into a party and you have a scene and pictures or movies of it, you have a conserved number of people unless someone comes in. So that is also conserved quantity that you can think about. You have edges right here. So I'll just describe a little bit what all these little components are. The edge function here computes message from these nodes and the edge attributes. So the edge has their own attributes, can be anything. In the planetary case, you can imagine the edges might be related to, say, Newton's constant, something that affects the forces, right? But we don't know what it is. This is something that the network will learn. And you have the receiving node right here and the sending node right here. So VR being receiving, VS being sending, U being the global variable again. You have the node function where you can update the node info from the previous node state and aggregate the messages. So you take in all the different, say, for example, in this n-body system case, you take in all the different forces from different nodes and add all of them up. It could be a sum pool. And then you start thinking about, how does it update the next node stage? And that's very important. And you train the network, of course, to predict the node states from T0 to T1. And all these edge function and node function is something that the network will learn as it looked at the data. So we don't know a priori what they are. Before I go too far, I'm going to say one more thing about graph network, how it relates to all the different other type of network. You can actually take this and do message passing to neural network, deep set. A lot of us is very interested in this recently. Relation network, non-local network. So I'm going to pause here and ask for questions. I know this is Zoom time, so try to see if there are questions first. I don't know if we'll see in the chat or not, or people can unmute. I don't know if they're allowed to unmute actually, Tetris.
Maybe I have a quick question. This is
Sure.
Luca. Which kind of features do you attach, like, these kind of problems, which kind of features do you attach to the nodes?
Which kind of features is in the nodes for, say, for the n-body system? So for the n-body system here, say for the planetary system, the nodes will have the features such as the mass, the positions, and could be the velocities in all three directions, right? The velocity in three directions could be the position. And if you're really pushing for it, you can also just have positions and as a function of time, and the network should figure out the velocities really. So it depends how much information you want to give to the network.
Okay, thanks.
No, this is a good question. Any other questions?
Andrew Price has a question on the chat. I'll read it out. Is this analysis sensitive to the time step? How does one assess an appropriate time step?
This is a great question, Andrew. So we actually did try several different time steps just to see whether it affects the equation and whether it affects what happens. And you will see actually that it doesn't matter too much if your equation that you found is the true equation. So there are many equations that you actually end up finding, or the system will end up predicting. But when your network really finds the truth, it tends to be, it doesn't matter at all. But for our case, it's much more obvious because we're finding a physical law that is basically universally correct in classical mechanics. But I would imagine there are other systems where you will need to make sure that the time steps have covered enough the frequency so that you can actually figure out the correct dynamics. So imagine if there's a person jumping, right? So if you don't sample enough when it's jumping, you only see it on the ground and never see the person jumping. So you will never be able to model the person jumping. You can only model the person like standing. So you need to sample it with enough frequency to, depending on the event, really. Any other question?
I have a question.
Please.
It's more related to the first to research about using neural networks to understand physics. Just as a link between like how human understand physics and how physics exists. Isn't that we kind of dumping the physics itself? Like a human can develop understanding of physics, basically more evolutionary perspective. What physical probability exists in the world that's important for our surviving, while physics itself is more structured. So thinking as neural network, like learning physics based on people will understand the physics this way, and the neural network understands physics that way. So this is a good thing. Isn't it better to restrict like learning physics from physics directly instead of having, weak links through humans or something?
I didn't quite entirely understand the question, but I do see your point is saying that, humans took millions of years, probably longer, to try to understand physics by, evolution and try to understand it. But I think the network's also spending a lot of time actually training, and given the right, particularly catered, curated data set to learn one particular situation, right? So it's more like
physics. Is it the same physics? Like from like the video for like, will this structure fail or something like that? Is it the same physics? Because like if we judge physics or the physical structure failing or not based on if human will think it, this is human physics, not physics.
I don't know.
I think maybe let's take that question offline. Thank you very much, Mohammed. Anyway, but we have a tight schedule to follow.
Okay.
And I really want to hear the rest of Shirley's talk as well. Thank you, Mohammed.
Thank you. But yeah, I'll be happy to talk about later too.
Sure.
All right. So the rest of the talk, as Tajun was saying, is a tight schedule. The planetary interactions. So we talked about here earlier with that. We just actually gave you the positions and the mass for any pair of planets as an edge. So it's a fully connected graph. Each edge is a function of two nodes. The update on each node would depend on all the edges active upon it, right? So all the edges could be all the forces. This is analogy to the Newtonian mechanics here for the graph network that we built. For those who are very familiar with graph network, you probably think it's obvious why you want to do planets with it. But for those who are not, this is pretty illuminating, I think. You have the data vector here. You've built a fully connected graph. So you have nodes and pair of nodes representing particles and two interacting particles with each other. You have the edge model, which in principle can compute the force law, but as a network, you didn't know ahead of time. You have the messages, and then you pull all the messages together, which is very similar to summing over to all the net force to each of the nodes. Once you concatenate with the node, which you have now the information of the masses and the positions of the node, you can easily compute the acceleration step and update the nodes. And the whole thing, of course, is trained according to what the data set is. And what we did, which is kind of different, apart from just graph network part, is that we encourage sparsity for both of the edge model and the node model. So when you encourage sparsity, you are able to approximate with symbolic regression later on, because otherwise the search space is huge, as I mentioned earlier. So outcome, does it work? It works pretty well, actually, for this system. It's a 1,000-step rollout. It's not just, and we only learn one step at a time. So the fact that it ran actually 1,000th step is actually pretty impressive. We also have truth on the top and model in the bottom. You can see the balls bouncing within 4 walls is really difficult to model. It turns out that's actually one of the hardest systems to roll for us to do because it's so chaotic. A tiny error on one step, it's going to explode quickly. And then we have done this zero-shot generalization also to larger system, where the network has never seen an MBOS system, say, with that many particles or that many balls or that long a string. And it also worked out really well. So when, as I was hinting earlier, if the rule that it found, at least for the network, works for real, it actually generalizes quite well to larger system. So now let's concentrate on the fact that we have predicted dynamics very well. We want to make sure we can extract the symbolic equation. So I mentioned earlier that we want to encourage low dimensionality representation right here so that we can extract the force laws. It can be any laws. It could be the molecular dynamics you don't know about. But what we did here, let me just quickly go through it, is that, say, when you record all the messages, you are trying to do something to make sure there are very few message elements that are important, so that when you feed it to the symbolic regression, you're not basically feeding a million elements to search for. So what did we do? Given the input simulation was 2D for one of those systems, we did not expect the dimension of the edge vectors to be much larger than 2. So we tried to eliminate at 2 first, and then it actually immediately makes the training a lot longer and the performance not as good. We have guesses of why that's the case, but you can ask me later. We try a bunch of different regularization. This is really just trial and error, and found that L1 works the best in this particular case. We have actually a different project right now on turbulence predictions. And that actually turns out that L1 regularization doesn't work as well either. So that's a different paper that we can talk about when we wrote it, when we finished writing it. And then we push the edge element through the symbolic regression and see what we can fit for the 2 elements. And the cool thing is we actually do find the rotation of a true force here for both elements. So the element 1 is a rotation of the true force when you add the element 2 together. We found force laws and we cover them from all the observed systems that we tried. For example, the Springs law in 2D and one of our R-square law in 3D. These are the 2 systems we try significantly. So we decided to do something harder because people were asking us, why are you doing something easy? Because you already know the force laws a priori. So we tried. So we tried something that we do not know the answer ahead of time. So here is a dark matter simulations with hydrodynamics, which means gas are involved and dark matter is involved, and they're evolving forward. This is about 3 billion years after the Big Bang. And looking at this, you ask yourself, can I predict, basically, my question is, can I predict the central density of one of these halos? This is explosion of a supernova, for example. One of these massive cluster halo, what's the central density of it? If I give you the information about the halos, which are a cluster of galaxies around it. So that's a question. What is the density of dark matter within the center of dark matter halos? Dark matter halos just really cluster of galaxies, given the surrounding halos. We can make guesses of what this answer may be, but we do not at all know this analytical formula from any previous work. So that's what we're going to try to do. We take these detailed simulations. Now it's a 2D version for you, but it's really 3D what we did. We found all these dark matter halos. We did a graph network, in this case, a unidirectional graph. We're all pointing to the same central density or central halo. And we try to extract a known dark matter overdensity equation. And we did that. And we found a new analytical formula that can fit to the observable better than what we can fit using, our physical intuition. So when I say, it's really what we just came up as physical intuitive versions of this. And you can see the error bar, of course, constant is not going to work well. This fairly complex version works okay, right? And if you allow it to use mass, which is what the simple version allows to use, and you can see that we actually drop the errors quite a bit. And this is something that we so far have not been able to explain ourselves why this is the case also. So it's something to be, to be resolved and try to understand why is this equation correct. So we have extract a phenomenological equation basically out of the system. For understanding though, I think we still need the human scientists to work on it. How about using some real data? So we talked about doing all this with simulations, but with real data is much harder in principle. We took the NASA Horizons Ephemeris Systems data that has orbits for 31 bodies in the sky for 30 years. And we took that and put it into the graph network you've seen earlier, we immediately recovered the symbolic regression. We used symbolic regression, recovered the Newton's law, which is super cool. And we also recovered the masses, the learned scalar quantities here, which are the masses of the bodies, the moons, the planets. For example, here, on the left, we show the bodies of the inner solar system. On the right, we show the same bodies evolved from the same initial conditions with the learned interaction. And you can see that they're basically exactly the same. Even better is that, we show the true masses versus the predicted masses of all the planets and the moons that we actually have looked at. The truth here is the blue star. The predicted one is the other one. And you can see that some of them has bigger error bar than the other. The ones who have bigger error bars, actually, for reasons, they're very good to have big error bars because they're very small compared to the major interactions of the system. Say Mercury is very light compared to the sun and all the, like Jupiter and all the other ones. And then all the other ones actually fit super well if they're not like super light in the system. Well, the Hyperions are really small moons, for example, so you have huge error bars, so is Phoebe. But this is all from a network which has never learned Newton's law. It figured out Newton's law and it figured out all the masses of the planets. So I think it's pretty cool. Conclusion: human interactions and physical intuitions really help us create new ways of thinking how to do machine learning. In this case, the graph network, this idea of why you want to parse things into particular objects before interacting. That's actually something that created graph network. These new ways of doing machine learning, such as graph network, help us simulate what we see in the real world way faster. What's more intriguing, at least for me, is that even for physical laws we don't know the answer to, we can observe the system and let machine learning help us find analytical expression. And thank you. I'll take questions here. I see a bunch of questions.
Fantastic. Thank you very much, Shirley. There are indeed a couple of questions in the chat. First one from Marcus. For many physical laws, you have natural constants playing an important role. Is your system capable of learning them from data as well?
Can you say that again? Sorry. There's a formula.
So for
yes.
many physical laws, there are constants. Yeah, can you learn those constants?
We learn the constants, actually. This is one work that we actually learn all the constants and learn how the model, like basically what the form is like, not just the constants. Many people ask us the difference between our work and I think Max Tegmark's group, but Max Tegmark's group does not do that at all, actually. If you look at the paper, we actually will find the constant and the form and basically what components it's supposed to be going in, which we do not dictate at all.
Marcella has another question. Is there any problem with sparse data or various time steps? For example, because of weather, some scheduled observation is not possible, missing, or yeah.
Yeah, this is a great question. We personally have not tried this on a very hugely like sparse data where like lots of things are missing. Because as I said earlier, if you're sampling a sinusoidal situation, if you don't hit the right frequency, you will always miss basically the sign, right? So this is the same problem as jumping people. You know, if you never record the person on top, you will never see the jump. So you need to make sure that's actually recorded somehow.
Probably one last question. Misha asks, have you tried to predict the symbolic equations using CNNs, convolutional neural networks, such as using a video stream or using graphical representation, rather than a graphical representation?
So this is the hard part. This is sort of the work next thing we might try to do. Our group has been thinking about how to push closer the neural net and the symbolic regression part together so that you can actually extract an understanding of the network. Right now, if you take, say, a CNN, you have a million weights. So how do you sparsify it successfully? I think that's the hard part. And I think that if we can do that properly, that will make the symbolic regressions possible. Miles Kramer also had made first, I think, public and free symbolic regression package out there. So try to use it, and it's really possible, I think, to extract some understanding of the network if you don't have too many elements right now. So the hard part is to search this huge parameter space. Not to remember all the mathematical functions, you can let it try.
Thank you very much. With that, let's thank Shirley again for a very inspiring and wonderful talk.
Thank you so much.
And we move on to the next speaker. Thank you, Shirley.
All right. Hi, everyone. My name is Luca Carlone. I'm an assistant professor at MIT, and as a co-organizer of the workshop, it's a great pleasure for me to introduce our next speaker, Courtney Mario. Courtney is a principal member of the technical staff at Draper in the Perception and Autonomy Group. For those of you who are not familiar with Draper Labs, Draper has supported NASA and other commercial space companies, starting from the design of the guidance system for the Apollo mission to other programs, including the International Space Station and the Space Shuttle. Courtney has over 11 years of experience in vision-based navigation systems. Since 2014, she's been a member of the Natural Feature Tracking team for OSIRIS-REx, and her other work at Draper has involved developing visual inertial systems for GPS-denied applications for ground vehicles, UAVs, and pedestrians. Courtney has received a bachelor and master in mechanical engineering from Tufts University, and she did her graduate studies with the Tufts Automated System and Robotics Lab. So Courtney, thanks for being here, and the stage is yours.
Thank you, Luca, and thank you for the opportunity to be here today. I'm going to share. And thank you, Shirley. That was a really interesting talk.
Thank you, Courtney.
Yeah, as Luca said, I've been at Draper now for almost 10 years, working on a lot of different vision navigation systems, everything from UAVs and autonomous driving, and more recently have been heavily involved in space development, working on the natural feature tracking team for OSIRIS-REx and leading a lot of the ground testing development there, and then more recently have been leading our algorithm development at Draper for our lunar precision landings. And so today I'm going to talk about some of just the challenges and considerations when developing vision navigation systems for space applications, and some of what we did on OSIRIS-REx and some of the lessons learned from that work as well. And so as part of that, I'll just kind of talk a little bit more about vision navigation systems and the challenges specifically for space missions, and then share more about the OSIRIS-REx mission, the algorithms that we used for that, and our feature development strategies, and then our mission results and lessons learned. So at Draper, we do a lot of different vision navigation development, and this is from typically GPS-denied environments, so anything like indoor navigation or urban environments or space where you don't have GPS, to military applications where you can't necessarily rely on GPS because someone may be jamming or spoofing you. And so in this case, we're using typically opportunistic features where we're tracking them from image to image and combining them with IMU data in a filter to compute a navigation state update. And then there's in certain environments where we have pre-existing images, so satellite imagery or other map data, we also define what we call known features. And then when we can match those from the map data into the camera images, those provide an absolute update to further constrain our navigation error drift. And I think what we can all probably appreciate with people who develop these systems is just how much when you take these systems out into the field and you're working with real hardware, how that's really where you learn some of the sensitivities of the algorithm, especially where outlier rejection is so critical to the success of these systems, and making sure that false matches really don't get into your filter for state updates. And it's really once you're taking it out and working with the fielded hardware and the cameras and the expected lighting conditions and other image conditions, that's really where you find out how well your algorithm works and get to really understand its sensitivity. And that's really beneficial for developing for terrestrial, for Earth applications. And it's one of the challenges for space development, because you primarily need to develop your algorithms on the ground ahead of time, usually mostly with simulated data, and kind of finalize your code and then put it on the spacecraft. The spacecraft launches, and it's not until you get to whatever planetary body you're going to that you really get to see the images with the camera. And it's really even not until you're doing your final descent that you get to actually see the images under the final conditions. So I think that's one of the challenges when developing for space. I think that's where experiences from terrestrial testing really helps you define your development plan for space, but it makes for, I think, kind of a fun challenge when you're developing for space applications. And I'll talk more about how we tackled that for OSIRIS-REx. So specifically for vision navigation for space, vision navigation has been used in space for years. I think some of the first missions were in the late 60s for Mars, but typically these are always with ground-based vision navigation. So the spacecraft will take images on board the spacecraft, those get downlinked to a team on the ground. That team then does all the image processing and kind of confirms that there are no outliers, and then sends up the navigation state back to the spacecraft. And typically these are situations where the spacecraft really doesn't require any real-time navigation updates. They're not doing anything critical where they need that in real time. And so that image processing can all be done on the ground. But more recently, when you think about some of the increased science goals, those really require increased navigation precision and getting real-time navigation updates to be able to land in more hazardous environments. So if you look at these images here, on the left is the Jezero crater where Mars 2020 landed. And in that case, JPL's lander vision system was able to land the rover right in Jezero crater, which was really interesting from a science perspective. And it saved what would have costed a lot more for them to land the rover miles and miles away in a safer area and have the rover traverse all the way to Jezero crater. And similarly on the right is where we ultimately ended up collecting the sample from for OSIRIS-REx, and I'll talk more about this, but you can see in the middle there is the graphic of the spacecraft and just how hazardous that environment was, which was really attractive from a science perspective, but very challenging from a navigation perspective. And so some of the challenges for developing these systems is that because of the high cost of developing these spacecraft, and they're potentially on the order of $1 billion, they go through a very rigorous testing and validation process, which means that the algorithms that are on board the spacecraft need to be deterministic. And so from a computer vision perspective, this means we're limited to relatively simple approaches and some of your more classical computer vision techniques, and trying to avoid some of the more black box in nature algorithms to make sure that when you get a result on board the spacecraft, you have a clear understanding and kind of pass through the software that you can say, yes, I know exactly why that happened. And then, so kind of the general approach there is sort of really simple algorithms, and then really test and make sure that the data going through it, that you're feeding to it, will work well for the spacecraft. But that's where another challenge comes into play, in that we're really limited to be able to test in the space environment before the algorithms get used. So in many cases, especially for these landing type scenarios, it's really only when the spacecraft is descending for that very first time that we get those images to actually do that testing. And so how do you test enough ahead of time without those images and those image conditions, and have confidence that it's going to work for real on the first time, when you really have no margin for error? Otherwise, you put the entire spacecraft at risk. And then the last challenge is the fact that when we're developing, we're really, the space hardware is radiation hardened. And so that means computation power is relatively limited. And unlike for terrestrial applications and embedded platforms where you can be processing hundreds of features at very fast frame rates, usually we're very limited in what we can actually run on board the spacecraft. So that's another challenge in developing these algorithms as well. So now I'm going to talk a little bit more about the OSIRIS-REx mission and what our algorithm was and everything we did for that development. So the OSIRIS-REx mission is NASA's mission to collect a sample from the asteroid Bennu. The spacecraft launched in September 2016 and arrived at Bennu in 2018, and then spent over 2 years orbiting Bennu and collecting images and LiDAR and other data to study the asteroid up close, and for the team on the ground to identify where we wanted to collect the sample from. And we ultimately collected the sample this past fall in October 2020. And so based on where the asteroid was at the time of sample collection, round trip light time at that time was 30 minutes. And so that meant the spacecraft needed to be fully autonomous during the sample collection phase, because if anything goes wrong with the spacecraft and it needs to be redirected, there's essentially that 30-minute lag before we find out something's going wrong and being able to redirect it. And so the spacecraft needed to be fully autonomous to handle all that on its own. The other thing with Bennu is, so down here you see the data we had ahead of time of what we thought Bennu would look like. So we had ground-based radar, we had estimates of what the surface would look like based on other similar asteroids, and we thought it would be relatively smooth. So we designed our navigation systems for a 25-meter radius sample site. But unfortunately, once we got up close to Bennu, we actually found it was a very rugged surface with a lot of massive boulders, much larger than the spacecraft, really just very jagged shape. And that 25-meter radius sample site did not exist anywhere on the surface. And so originally the primary navigation method was actually a LiDAR-based approach, and our vision navigation method was originally a backup, and that our system got upgraded to the primary method because of the increased precision that it provided, and because the sample sites we were looking at are on the order of about 10 meters in diameter as opposed to that 25-meter radius. So this is just a close-up look of the final down-selected sample sites. So we down-selected to 4, and you can see the sample sites in these areas are the circles where they're typically pretty much all about 10 meters in diameter. And the one we chose was this Nightingale site on the left. And you can see it almost looks, in some cases, like the most hazardous of the 4, but it was chosen because it seemed to have the highest likelihood of getting the best sample. From all the science data we had, the team really thought that the material at that location was the best, most sampleable, and would be the most interesting to study. But if you look at the bottom and kind of the rocks that are in this area, this is a visualization of just the scale of those rocks and how hazardous those are to the spacecraft, and basically what we were asking the spacecraft to do in this case. So for the algorithm we use for navigation, we use Lockheed's Natural Feature Tracking, or NFT. And so NFT operated autonomously for over 4 hours from 500 meters down to the surface. So it started at this orbit departure maneuver and navigated all the way through. It autonomously, so it not only computed the state, the spacecraft state, position, and velocity, but it also propagated ahead to some of the key kind of epochs along the trajectory, which are these checkpoint and match point burns, so that the spacecraft could compute the magnitude and size of those burns to be able to ultimately orient the spacecraft so that it was pointed normal to the surface at the time of touchdown. And so the spacecraft never actually landed on the surface. It just had, and you can sort of see it here, and there's later images, but it had just a sample arm with kind of a drill on the end that touched the surface and kicked up material. And then after it detected that contact, the spacecraft backed away. So NFT operated for this entire duration, processing an image about every 2 minutes for a total of 30 images throughout that entire time. And the way it works is it has, NFT on board had a catalog of known features that we had defined during earlier mission phases. And for each of those known features, what's unique about NFT is that it actually renders the appearance of those 5 features for the image. So using the predicted state of the image and then the estimated sun vector at that time, it could render the expected appearance of those features. And then using those rendered features, it would match those to the image using normalized cross correlation. And based on where it matched in the image, those locations would get used for computing the state update. And so I want to talk just a little bit more about features, because I think feature can be kind of an overloaded term. And so in this case, when we say feature, we mean really a patch on the surface that gets defined at various sizes depending on where you are in the trajectory. And we defined features to cover our entire, both the nominal trajectory as well as any 3 sigma dispersion along that trajectory. And originally estimated that it would take about 300 features. We were able to do it because of the trajectory design with about 100 features. And so then the feature itself is made up of shape model data. So the shape model data was built during earlier mission phases from all that orbital data we were collecting. And so the feature had a layer of displacement values that gets used to define the topography and terrain of the feature, and albedo, which defines how light reflects off the surface. And so then for each feature, we render the expected appearance and we correlate it against an image search region, which is sort of where we estimate the feature to be in the image and some region around that based on our uncertainty, and we get a correlation surface, and the highest scoring peaks from that correlation surface are what get used for the navigation update. And so in this case, what's important is that NFT applies a threshold to the correlation surface and only accepts peaks scoring above that threshold. So really, because we were only using 5 features per image, both the feature selection, so making sure we selected unique terrain that wouldn't have false matches but could score well, as well as the shape modeling process and the algorithm they used and the ability to represent the surface, both of those were really critical to our success for NFT because we really had no margin for outliers by only processing 5 features per image. So we spent a lot of time trying to characterize what makes a good feature. And we spent years, even before we arrived at Bennu, we spent probably 5 years using simulated data and then even some of the early Bennu data. And what we were really looking for from a correlation perspective was that, so in this plot here, we have the correlation score on the x-axis and the pixel error on the right. And this is a result for a single feature on several different test images. And we were really looking for high scoring correlation peaks with low pixel errors that scored above NFT's score threshold. And then any secondary peaks, which are the red and yellow points here, were lower scoring and nowhere near at risk of being above this threshold and being accepted and used for an update. So that's really what we were looking for. We did all sorts of testing, especially also with the shape model data and even working with simulated data from that to try to understand how that shape model algorithm works on different terrain. And one of the things we found is it tends to smooth the edges of certain terrain features, especially larger and higher, like steeper slopes. And so we tried to stay away from taller boulders, which was kind of a challenge given Bennu's rocky surface. But here are just some examples of the shape model results. So this is an example of something that ended up being a strong feature where it was a really uniquely shaped rock that was relatively flat. The shape model didn't necessarily, like if you look here and versus the image, it didn't necessarily get the terrain exactly right where all the shadows weren't necessarily correct, but it did the albedo variation, it modeled well, and that ultimately really worked well for us for correlation. Whereas this example here was a much larger rock, and essentially the slope of this rock ended up kind of bleeding into the terrain around it, and that really hurt correlation to where we got a lower scoring peak with larger pixel errors. And we also did some studies that I won't go too in depth in, but basically looking from the images. So we had done a lot with simulated data trying to autonomously select features, and we had it tuned for what we thought the surface of Bennu would look like. But then once we saw the actual surface, none of that really worked. And so we did do some studies with Bennu trying to characterize the shadow and the feature content for what makes a good feature, and we found some metrics there. But that was kind of an example of where simulated data really doesn't necessarily help when it doesn't match what you're actually going to see in the images. So I want to talk a little bit more about just the actual flow of the feature development and then our testing and evaluation process, because that was really critical to NFT's success. So from a feature development standpoint, and again, we ultimately did this for on the order of 100 features. We started with the orbital images that we had from those 2 years of orbiting Bennu. And then the shape model team had been using those images to be building lower resolution shape models. And so from those images, we selected what we thought would be good features and sent those locations to the shape model team to be building those features. And then once they had the features, we then tested those, and I'll talk more about that later, but essentially from our evaluation, if the features worked, then we put them aside for going into the feature catalog. If not, then we would sit down with the shape model team and show them what wasn't working. In some cases, they would say, yeah, we think we can keep improving that, and they would spend more time refining the feature. In other cases, they would look at it and say, no, that's really the best we can do. And if it was a location where we needed another feature to be able to have the coverage we needed for the trajectory, then we would go back and try to select a new feature and repeat that process. So it was a lot of that kind of back and forth and to get the final set of features that we needed. And then once we had that, we optimize the order of the catalog to make sure to try to prioritize the features that scored best, but also we needed to optimize not just for the nominal trajectory, but also our 3 sigma dispersion. And we wanted to make sure that those 5 features per image were spread well across the image. And so then we also did 2 different spacecraft rehearsals. So this was where we took the spacecraft from along the final descent trajectory, and it navigated itself using NFT to those checkpoint and match point burns, so about 150 meters above the surface. And those rehearsals provided the first images that we had that really reflected the final image conditions to know how well these features would work. And so in some cases, we found that some features didn't score as well for those, so we reordered the catalog accordingly based on that. And so all of that took on the order of a year to do all that for the final catalog that we used for sample selection. And so then for the actual testing and evaluation part, this is where, so we took for each feature, we rendered and correlated against all the images that we actually had available. And from those correlation results, we kind of dug into them, and this was a very tedious process, but ultimately what we needed to do because the feature performance was so critical. So what we did was kind of feature by feature, we went and looked visually at the renderings of the features for the quality to end with the score, and trying to look and understand, okay, how well did the feature perform? How, if you look at the rendering, can we see why it may not have scored as well? Is that something about the image condition? Is that an image condition we don't necessarily expect to see on the descent? So it was a lot of kind of looking, okay, here's the data we do have versus here's what we expect, and how do we think it will perform on the descent conditions? And so this, just to give you a sense of just how tedious that was, this was just one feature, and all the test image results that we did have for it, which was a total of about 16 images. So this is those 16 images in 2 rows, where in each case, the top row is the image subsection, and the second row is the rendered feature. And if you look, you'll notice that even within these 16 images, a lot of the test image conditions are repeated. So even though we had 16 images, we really only had even on the order of 7 unique image conditions. So we didn't have much to work with, but this was, we ultimately, for this feature, we found that some of these renderings here, where you see the albedo is really overexposed, that was representative of what we expected for the sun angle. And so this was a case where because this feature performed well for these situations, we had higher confidence that it would work well for the final descent. So then for the actual sample collection, the spacecraft successfully navigated and collected a sample in October 2020. You can see here on the lower left are all the images that NFT processed and the features that were used. And you can see just the sense of how the terrain and some of the challenging image conditions, especially along the spacecraft, flew during the trajectory. And we had some outages where we didn't process features at all just because of the challenging image conditions. But for all the images we did process, we successfully matched every feature, and NFT ultimately navigated with an error of less than 3.5 centimeters in our final contact location, which you can see here. So this is that spacecraft arm that touched down and collected the sample. This was less than 1 meter from the original target location within that hazardous area. So as tedious and time-consuming as that feature development process was, it ultimately worked well and allowed NFT to successfully navigate. So just kind of a few takeaways from all this. I think one of the key things when you're thinking about developing these systems, it really comes down to knowing the algorithm that you have on board, and the algorithm sensitivities really dictate the rigor and the level of ground testing required. So in our case with NFT, being only able to process 5 features, and also with how it rendered the shape model features, that really required us to scrutinize each feature individually for the entire catalog. The other part is understanding the feature source data and the surface modeling techniques. So for a lot of these missions, they tend to rely on various shape modeling techniques to be building the map data of whatever planetary body you're going to. And so understanding what that shape model method process is and what are the pros and cons of that algorithm and how it impacts terrain modeling. And then building margin into your ground testing target metrics. So in our case, when we tested all the features on the ground, we actually really pushed them to score even higher than what we knew NFT threshold was. And that allowed us for, if we expected correlation scores to decrease for the final image conditions, we made sure that even if they decreased, they were still above the NFT threshold. And then the last part is just that with a lot of these missions, they often consist of teams that are scattered all across several different organizations. In our case, we were working with 5 different companies at least that were scattered across the US, plus other organizations in Canada. And the fact that we had spent probably on the order of 5 years working together for the development of NFT before we really started the final feature development for the catalog really made a difference for us to be able to just come together and work well when we really needed to for NFT and the sample collection. So with that, I want to thank the entire Cyrix's team, because without any of them, this entire mission wouldn't have been possible. And it really was a fun project to get to work on and fun to see it all succeed. So any questions?
Catherine, thank you so much. Great presentation, very, very interesting. We might have time for a couple of questions, and I think there are a couple already in the chat. So Marcella is asking something that probably you partially covered, but let's see if you have more comments. She's asking about the validation and test process, in particular in these cases in which you have very small data sets, like to test on. Is that purely simulation? Can you say a little bit more?
Yeah, so that's a great question, because that's really one of the challenges. So in our case, we relied a lot on simulation ahead of time and kind of learning and doing sort of validating that our entire ground process at least worked. So everything from the shape model development through to NFT features, and showing that that all closed for simulated data. And from that, also learning what we could from the simulated data about the shape model performance. But then when we actually got to Bennu and we had the limited data, that was where we used the limited data that we did have to actually kind of go back and compare the performance of those features with the Bennu data that we had against some of our previous simulation results, and kind of make sure that some of the conclusions and approaches we had drawn from the simulated data still applied, or in certain cases we had to adapt. But that is really one of the challenges. That's also where doing those spacecraft rehearsals were really critical. And so having the spacecraft navigate to just below the surface and backing away before it actually contacted the surface gave us those images with the final expected conditions that were really useful.
Perfect. Okay, thanks. There is another question from Andrew, who is asking, you mentioned that the features were sourced from 7 unique images. Could you expand on how these images were obtained?
Sure. So yeah, so the features were defined from, so we had all the orbital images that were collected from kind of the 2 years there's a whole suite of science cameras on board the spacecraft with different field of views to be collecting images at different resolutions. And so from those, that's how we look, because of the timeline of the mission, the shape model data at that point was lower resolution globally than what we needed for the features for NFT. And so it wasn't possible for the mission to build the entire asteroid model at the resolution we needed. So that was where we needed to select the features from just the image data and look at basically from the terrain and what we thought would work well. And then the shape model team then used those images to further refine their model. And they used what's called stereo photoclinometry, which is kind of a combination of both stereo and photoclinometry techniques to solve for both terrain and albedo. So it was kind of all those orbital images were then used both for our feature selection, the shape model generation, and then ultimately our testing of the features.
Great. Okay,
and
so
those
we're running. Go ahead.
I was just going to say, those images, there's asteroidmission.org is the whole project website, and there's all those images, and there's a lot more there too that you can look at and use for development.
Thank you so much. I actually had a bunch of questions about ransack and outliers, but I'm sure TJ will stop me because otherwise we'll run out of time. So we stop here and we'll take my other questions offline, but thank you so much for the presentation.
Sure, thank you.
EJ, back to you.
Bo's turn, actually.
Hello. Hello, everyone. My name is Bo Chen. I'm a researcher from the University of Adelaide and the Australian Institute for Machine Learning. In the coming up section, one of our organizers, who is also a generous sponsor of this event, Marius Kramavicius, will bring us a special demonstration of Black Swan's mission design simulator. Marius has profound experience in aerospace engineering. He has helped the system engineering and mechanical design for the second Lithuanian satellite and has worked at the European Space Agency on technologies for the ISS and the XO Mars mission. He is now the founder and CEO of Black Swan Technology, whose mission is to develop autonomy-enabling software in space. Welcome, Marius. The screen is yours.
Thank you, Bo. Hi, can you hear me?
Yes, I can hear you.
Great. Let me just share my screen. All right. I hope you can all see this. Okay, so I want to welcome everybody again to this workshop focused on applying AI in space. I think we already had two great keynotes from Shirley and Courtney, and our team is looking forward to seeing the presentations from the participants in the next session. So at Black Swan Technologies, as Bo mentioned, we are building autonomy in space and currently targeting the growing in-orbit servicing market. MDS, the Mission Design Simulator, is our flagship product. We designed MDS for our own needs, basically to develop in-orbit servicing scenarios, and actually discovered in the process that it could potentially be useful to others too. So we started MDS with, started sort of testing MDS with a small group of researchers, such as yourselves. And thus far, people have used it for generating synthetic data sets, prototyping and testing, navigation algorithms, as well as preparing exam tasks for undergraduates. Since my team explicitly told me not to turn this into a sales pitch, I will be brief and show you what MDS does, referring to a specific scenario we have created for ourselves, and actually let you decide if MDS could be useful for your own work. So I will start demonstrating the basic features. MDS can be run in both currently Windows and Linux machines. And as you can see, it has a graphical user interface. So let's say we can start with setting up a specific scenario, which is a target chaser scenario in our case. And let's say that I want to change the inclination of my target object. So you can see when I change the values of the inclination in degrees, I can see the results being propagated straight away. You don't have to wait for any sort of calculations. And if you're familiar with some of the industry standard packages, that's the case, and it's not the case in MDS. I can also go ahead and add more simulation objects. So let's say for this scenario, I want to have two target objects. So I can go ahead and add the second target object. And I want to also change the inclination of it to 45 degrees and perhaps increase the orbital attitude to 9,000 kilometers. Then I go ahead and press run to run the simulation. I can also speed it up. And slow it down using time multiples. So this allows me to see what's going to happen in the future, and that helps the mission design. We also have these standard tools such as the ground track, which basically shows you the 2D projections of the simulation objects on the screen and the simulated camera. That simulated camera is on board the Chaser spacecraft in this case, which is the bigger one. But it can be from the video feed, it could be from any sort of object that has a simulated camera in the simulation. And as you can see also, you can easily switch between the different views. So the main view is the view of the Earth, sort of overview, where you can see the orbits. And then I can go ahead and switch into the view of the chaser, also the view of the target. I have two targets in this case. The one is higher than the other. And you can see that reflected in the main window. The interesting thing is actually also you could control the objects that have actuators attached to them. So let's say in this case, the chaser has reaction wheels and thrusters. So I can just control them with my keyboard, just like in a computer game. Okay, so then we have an API, a gRPC-based API, which is currently implemented in Python. And you can do basic things like pull telemetry data from the API and control the actuators of the objects that have actuators assigned to them. So let's say, I don't think you've seen this, but I can run and enable the thruster and then disable the thruster at a certain time. And you can see this working in the simulation directly. I can also do something more interesting, which is controlling the writing control algorithms and controlling the objects externally. So in this case, the target object has a robotic arm, and then I can, by using the API, I can extend the robotic arm and retract the robotic arm. But it could be any sort of script that works through API, connects to MDS, and then controls the actuators in the simulator. So in addition to MDS, and I'm going to try and make this as smooth as possible, we also have the image generator, so which is called the Baker. And basically what the Baker does is it generates synthetic image data sets. So that serves a specific purpose. I just have to relaunch it. Give me a few moments. Right, yeah, so basically you can generate synthetic image data sets with the Baker and then use it to train your computer vision and deep learning algorithms. In this case, you could set the image size, you could set the for this specific target chaser scenario, the distance, the minimum and maximum distance between the target and the chaser. You can also set the orbital parameters for the chaser and of course, adjust the field of view. I can also adjust the amount of images that I need in the data set and go ahead and press play. The generation process begins. You can wait until this amount of images is generated. You can always press stop and go ahead and view your generated images in a dedicated folder. So you have the image sequence here that was just generated, and also have a JSON file with the ground truth. That file contains all the orientation and position, also the bounding box parameters for each image in the sequence. Okay, let me then go back to MDS. So coming back to MDS, our currently highlighted scenario is the target chaser scenario, which is somewhat relevant, I think, to any sort of deep learning or computer vision research. So the rendezvous of two objects in space with the goal to make them perfectly aligned with each other. And to do that, you can run various object detection, segmentation, pose estimation, and any other vision-based algorithms in real time. So actually, let's go ahead and run our own object detection and pose estimation algorithm. It's going to take a few seconds to load the models. So this is connecting to MDS through its API again. And when I run the application, I can see the application windows being generated with the detection and pose estimation models running. And I can also see in the simulated camera, the result being fed to the MDS through its API. And just to prove to you that this is running in real time, I can also move the chaser object a bit, just to test if maybe the algorithm fails if I change the camera view of the chaser. And in this case, it hasn't. So that's great. Right. So once you rendezvoused with the object, once you're sort of close enough, you could perhaps do something that is a bit more interesting, which is to use a robotic arm to capture the target. So MDS also allows you to prototype and test robotic algorithms in real time. So if I run this sped up demo and enable the labels, you can see the navigation algorithms being resolved in real time again. Actually, and if I change the view to the target, and you can also see the inverse kinematics of the robotic arm. That's also being resolved in real time as the chaser tries to grab onto the target. And again, this is a specific scenario that is relevant to us, but it could potentially be any other scenario that you can think of. So hopefully after seeing this, you could also think of many other scenarios where the simulation capabilities we demonstrated would be useful. From the paper submissions, we definitely saw a few cases where, in our opinion, authors could benefit from using MDS in their research work. And just before I open for questions, I just want to quickly mention on the planned major updates of the software that we're planning to implement or implementing right now. So we want to actually increase the photorealism of MDS even more, especially the image generation part, also adding semantic segmentation tools. We're planning to add model import. So you could easily import your own models of different objects you want to simulate and run different scenarios with it. On top of that, based on the response that we've received from our early adopters, we're planning to add more physics models, such as flexible dynamics for modeling things like fuel sloshing and solar array flex and some other models as well. So with that, we're open to questions and would love to hear about your specific scenarios you would like to implement in MDS.
I have a question.
Yep, go ahead.
Thank you. Very, very nice work. First, you mentioned that there is already like researchers and companies that try to use this tools, but I think also, for example, in other simulation like Bango and another simulation, there mentions that the utilizing game engine for generating synthetic images or generating face releases specifically is actually not the same, and there is a lot of kind of considering this is not like the sensorial part is not valid. Another point also based on this is built by Unity, the problem with ray tracing or ray marshing or ray tracing algorithm isn't it like rendering before, like some other tool rendering with OpenGL would be better for this case instead of just rendering on the real time. But overall, thanks for great talk.
Yeah, for sure. Great questions. So the first one, we're definitely are aware of the domain gap problem, and we're going to be firstly increasing seeing how we can increase the photorealism of the current simulation, and also working with researchers to see how we can sort of close the domain gap as much as possible. I don't know if my colleagues want to add anything else.
Okay, then because of the time.
For the second one, just to quickly, yeah, I mean, the ray tracing is possible as well. You would probably not get a real-time performance in some of the cases, but we're definitely going to be adding that option as well to ray trace, because we looked at it before, but our sort of focus right now is prototyping, quick prototyping, and seeing your algorithms in action in real time, the way you see it right now.
Yes, and I would also like to add that for us, the big focus is the real time, because we want to train a VBN which is able to react to any situation that kind of happens there. So we want that reaction to actually happen in real time. Don't get the algorithm too much time to actually deal with it as it would in actual situation.
But also, okay, like if we train and develop a system based on this tool, would the system work when we try to deploy it?
Yeah, again, that's a good question. We're going to be working as we go along the development curve and actually testing those algorithms in space with actual in-orbit demonstrations to sort of push the simulation closer to the real world as much as possible.
Okay, sorry to interrupt here because of the time. Let's move on to our next section. And thank you again, Marius.
No worries.
Yeah.
Welcome also from me. I'm Pablo Gomez. I'm also one of the organizers, and we now have the first session on the spotlight presentations. And just as a brief reminder, we have 8 presentations, each is 5 minutes. I would ask the presenters to please try to stay on time to keep the schedule. There will not be a direct Q&A, but you will have, of course, the opportunity afterwards in the gather late to ask questions. And finally, I would like to apologize in case that I happen to mispronounce any of the names. I'm trying my best. And I think with that, we can already jump into the first one. The presenters will be given the right to share their screen. And the first presentation is on AI for dating starts, a benchmarking study for gyrochronology, which I think will be given by Roberto Javier Lopez Sastre. And Roberto, the floor is yours.
Sorry, just a reminder, and sorry for adding to the delay. There is a Best Presentation Award, so just to heap more pressure on you guys. Everyone, not just you guys, sorry.
Yeah, okay. I guess you can hear me. Let me share the screen. Okay. Okay, hello everyone. Yes, I am Roberto Lopez Sastre from the University of Alcalá in Spain. And this is a joint work with my colleague Andres Moya from the UPM in Madrid, Spain as well, and my master student Jarmi Recio Martinez at my university. The objective of our work is to be able to estimate the ages of the stars from gyrochronology data, right? So, so probably some of you are not familiar with this technique, right? So I'm just going to briefly explain it. Gyrochronology assumes that our stars spin more slowly over time, right? And it is believed that this is due to an effect known as magnetic braking, right? The technique itself is used for estimating the age of a low mass star, that is a star like our sun, from its rotation period, right? So as soon as the rotation period varies, we are able to prepare an estimation, a linear function that is able to regress the age for the star. So basically, this was proposed in 2003 by Sidney A. Burns, and gyrochronology basically allows for the derivation of these ages for cool main sequence stars, like I said, based on their observed rotation periods and masses. Or if you don't have access to this data, we can use a suitable proxy like color band and so on. So technically or traditionally, gyrochronology techniques have been fitting a linear expression containing, as you can see here, these three variables: the rotation period, the mass of the star, and the age. And having access to two of them, you can play to infer the other one, in this case, the age. But we want to change the perspective, right? We want to approach the problem from an AI perspective. And basically, our idea was to start learning some regression models from data. So for doing so, I'm forgetting about these linear expressions. So what we started was to start to collecting data from stars, where the age can be obtained in a very precise way. And then we started learning some AI models for regression, and then the benchmarking, standard benchmarking, where we compare the different, let's say, state-of-the-art methods in regression models for this new problem. Okay, and this is basically what we present in this paper. In this paper, we present our data set, our sample, which contains more than 1,000 stars with precise measurements of some stellar observables like effective temperature, logarithm of the surface gravity, log GT, mass, radius, and so on. We also provide rotation periods and ages obtained from asteroseismology and clusters observation of the stars. And this is something, this is one of the main contributions of the work, right? The data set itself. Once the data set was gathered, was collected, we started with the benchmarking work, training a set of AI models, right? Where we define clearly an experimental evaluation process with a typical training, validation, and testing splits. We provide all the code, and all the code is publicly available, so everybody can reproduce the results. And this is the battery of techniques we have been playing with, right? From linear regression to neural networks, and also playing with the stacking, which is a standard technique in AI for combining different models. And basically, in our experiments, we discovered that it was very nice to discover that these AI models are able to get errors lower than 0.5 gigayears in estimation, which was not previously possible with other linear expressions. And I hope you are interested in knowing more results, more details about our work, and we will see you on Gatherly.
Perfect, thank you. Then we can just move immediately to the second one, which I think is probably the paper with the longest title, and it's investigating spiking neural networks for energy efficient onboard AI applications, a case study in land cover and land use classification, which will be presented by Gabriele Meoni. Gabriele, please go ahead.
Yes, thank you. Can you hear me? Can you hear me? Yes.
Yes.
So perfect. What's wrong here? I have a technical problem. Okay, nice. So no, thank you. Yeah, 1 second. Sorry for my. Yes. So good morning, everyone. Thank you, Mr. Gomez, for introducing our work. So today we'll present basically our work on the use of spiking neural network for onboard AI.
I think we see your interface, like the presenter interface, rather than the full slide.
Okay. So 1 second. I'm sorry for it. Okay.
I think after you share, there should be a button like to switch the monitors, I think.
Okay, let's see. Can you see now?
No. Oh, no, yes.
Yes.
Okay, perfect. Thank you. So our work basically tried to use the spiking neural network for onboard AI. The reason for that, because spiking neural network have been demonstrated some interest for energy efficiency for static image processing, but mostly on some benchmark data set like NIST, for instance. That's a really interesting properties if you consider small satellites application, especially CubeSat, where you have they have really small energy budgets. So spiking neural networks might be of interest for some of onboard AI applications. The biggest problem with that is that basically the efficiency in terms of energy of spiking neural network on space data, and space application is not as been demonstrated convincingly. Some studies basically say that the more the data sets are complex, the more the gain in energy efficiency is basically lower. So our idea was trying to test basically and compare spiking neural network and artificial neural network for the land cover scene classification on Eurosat dataset, and also of course in terms of accuracy. So our methodology is basically the following: we train a model, an VGG16-1 on Eurosat. Then through a pretty standard approach to convert our artificial to spiking neural network, we perform AN-SNN conversion. Then we retrain the model in the spiking domain, and we use the methodology performed in Karo spiking to estimate the energy. So the conversion is pretty simple approach. It basically consists in taking every layer composed of a convolutional layer and ReLU and converting into the equivalent convolutional layer, spiking ReLU, integrating fires neurons, and adding a post-synaptic low-pass filter to reduce the activation rate. As regard the energy estimation methodology is the one suggested in Karo spiking, and they say basically is not really accurate, but the point is not really performing an accurate estimation of the energy, more than to compare the models in terms of energy in themselves. So the approach is this: for every layer, you can estimate the energy by summing two contributions. The first one is the energy per synaptic operations that can be easily calculated by counting the number of synaptic operations times the energy that you need for one synaptic operation. You do the same for energy for neuron updates, basically. So the energy for single operations basically are other dependent, and they are included in Karo spiking. And to estimate the number of neurons updates, you can count the number of neurons that you have multiplying times the number of time steps. Of course, for artificial model, the number of time steps is just one. And instead, for synaptic operations, it's a little bit more complex. So what you have to do, you have to count, you have to sum over the number of neurons, counting the number of synaptic operation averagely for every neurons, multiply times the number of time steps and the time step width, and multiply times the average input spiking rate. That's basically what makes the biggest difference, because if you consider for artificial model, it's basically just 1 divided times timestamp width. It's different for a spiking model where it's really data dependent. To reduce basically also the firing rate, we try to apply the private filtering. It's basically, if you consider the Eurosat images, the images are composed of especially for instance this one, like a spot of color that's pretty homogeneous one. And so if you pre-filter with the private filter, you can keep the information of color, but at the same time underline the boundaries. And so you have only the boundaries as basically fire. Then we train an artificial model on Eurosat. We train different spiking models with and without private filtering, and with different timestamps and timestamp width. And we perform the energy estimation on different hardware, including standard hardware, so various CPUs and GPU, and including different neuromorphic hardware, including Spinnaker 1 and 2 processors on the low heat. So the results are basically this, just to underline the most interesting one. If you consider the private filter and you deploy the artificial model on the basically on the GPU, you have a loss in accuracy, and that's basically pretty high also. It's like 10%, but at the same time, you have a pretty high, like 34 times gain in energy. But it's not only dependent on the hardware efficiency, because if you compare the models themselves on the same hardware, so on the low heat, still you have some gain in energy. So to conclude, yes, we still have a drop in accuracy that maybe might be compensated by using different time encoding, for instance, time to first encoding, or by using different models. But at the same time, we measure some gain energy efficiency. So to sum up, basically, our study is just to encourage further study to see if it's other benefits in terms of energy with loss drop in accuracy are possible. So thank you very much for your time. And of course, if you're interested, please try our code. And sorry again for me.
No worries.
No problems.
You're still right on time, actually. Then we can move to the third presentation now, which will be autonomous planetary landing via deep reinforcement learning and transfer learning. And I think it will be given by Julia Chabat. The floor is yours, once you have the rights to share.
Hi, can you hear me? Okay, I'll show my screen. Yes. Okay. Okay, can you see my presentation? Okay. Good evening. My name is Giulia Ciabatti, and I'm a master student at Sapienza University. going to present the paper Autonomous Planetary Landing via Deep Reinforcement Learning and Transfer Learning extracted from my thesis work in cooperation with NASA JPL. The purpose of this work is twofold. At first, we develop an open source pure Python embedded real physics simulator for planetary landing. Then we perform vision-based autonomous landing and domain transfer. To develop the simulator, we start from terrain generation, where available, such as for lunar and Mars environments, we utilize 3D meshes available on the official NASA GitHub repository. For Titan, since such meshes but not available, we reconstruct the terrain starting from star images retrieved by NASA's Cassini-Huygens mission. We then define the lander in the ROS URDR framework, and we provide it with for thruster for control, the camera, and a LiDAR sensor. Optionally, also a depth camera and a segmentation mask can be utilized. We have our problem as a deep reinforcement learning problem and define our model as a deep deterministic policy architecture, which allows us to better handle the large observation space and more inputs, and we execute the training on 2 lunar environments. We test transfer learning to evaluate the capacity of our lander to transfer the knowledge learned on other environments, and in this case, Mars and Titan. If this proves successful, it can be useful for solving robotics problems involving not well-known environments, and of course it makes the agent fully autonomous. Okay, this is a high-level block scheme of our model, which follows an activity approach, for which we assume a fully observable environment that can be modeled as a market decision process and a continuous action space. And these are the results. In the 3 training sessions, we see that after an initial installation, the agent learns quite fast and the reward increases rapidly, while in transfer learning tasks, after an initial oscillation, again, the agent tends to improve the reward as well, and these are executed only on 20 Hz. In these periods, where the top 2 were executed after the training session on lunar environments and the bottom 2 are relative to the main transfer, we see that the agent keeps the correct orientation and steady course, which means it does not flip over, and approaches the ground in a control fashion. We are currently working on 5 different neural network architectures, such as auto-critic and PD3, and physics into neural network, and we are adding also atmospheric disturbances such as gas and albedo, which is particularly significant for the Titan environment, for instance. And thank you, and see you at the presentation.
Thank you very much. And now we move to the 4th presentation, which will be improving astronomy image quality through real-time wavefront estimation, which will be given by David Thomas. David, please go ahead. I think we can't hear you yet, in case you
Hi, everyone. Yes, I'm going to be talking about improving astronomy image quality through real-time wavefront estimation, and I'm a PhD student at Stanford. So we're going to be focusing on the context of the Rubin Observatory, which is a giant telescope that's currently under construction in Chile. And starting in 2023, it's going to take a 10-year survey of the southern sky. This survey is going to help us answer a lot of questions, ranging from at the largest scales, the nature of dark matter and dark energy, to kind of closer to home, what's the content of our solar system. But the one thing these diverse science use cases all have in common is that they're predicated on keeping the telescope in focus. And the reason this is challenging is kind of analogous to your cell phone, actually. If you're trying to take a picture with your cell phone and you suddenly, flick it around, it has to refocus. And as we slew this telescope around, the mirrors warp and the alignment, gets perturbed, and the image quality degrades. And so we have to sense and correct that. And the way we do this is that there are 4 special sensors in the corners of the focal plane that are strategically out of focus. And so instead of getting point sources, we get these ring-like images because our primary mirror is an annular shape, and we call these donuts. And so the wavefront estimation problem is taking all these donut images from across these 4 sensors and estimating 56 coefficients, which completely govern the image quality of the optics. And the breakthrough in our work is that we split this into two highly tractable pieces. In the first piece, we use the CNN to make a local wavefront estimate from a single donut image. Then we aggregate all of those and constrain the global wavefront coefficients with least squares. Okay, so in the first stage, we generate over 600,000 simulated donut images, and we have a neural network that takes a donut image D in its position R and predicts these 18 local wavefront coefficients. So the first part of the network kind of encodes these 256 by 256 pixel images into a 1024 length vector. Then we add in the position, and then the final few dense layers take us to the local coefficients. So here are the results from this step. And on the left are kind of the samples we do worse on the right are samples we do well on. And while there aren't really standard benchmarks for this task, personally having worked on trying to develop lots of alternatives, I can say that even the results on the far left are kind of state of the art in some sense. And so the fact that as we go to the right, we're seeing a pretty big drop in the mean squared error between our estimates and the truth is really promising. Okay, so in the second stage, we take these local predictions, which we have at these 4 sensors, and interpolate the wavefront across the focal plane. So for each local coefficient, we fit 3 global coefficients, which define a plane. Okay, pretty simple. And we test this on 500 high fidelity simulated observations. And we find that for every single observation, this technique would lead to an improvement, and it reduces the global wavefront coefficients by 66%. So here is the PSF at the center of the focal plane, kind of a common metric for image quality. So here we have it before and after, so kind of the residual if you corrected out our predictions. And we find that the PSF full width half max is reduced by 27%, and the height of the PSF increases by close to 500%. Now, admittedly, this is just one component of the image quality, but on nights where the atmospheric scene is really good, this will be one of the limiting things for this telescope. And what's exciting about this conference is we're looking at space applications, and we think this method would also work well on future space telescopes that use large deformable mirrors. So thank you so much, and please come to my poster session if you'd like to learn more.
Thank you very much. And now we move to the next presentation, which will be on-orbit inspection of an unknown tumbling target using NASA's Astro-B robotic free flyers, given by Charles Oestreich. The floor is yours.
Hello. Pull my slides up here. So my name is Charles Oestreich. I just recently graduated with my master's degree from MIT, and presenting today on our work on-orbit inspection of an unknown tumbling target using NASA's Astro-B robotic free flyers. So just the problem overview, we talked a lot about relative navigation for rendezvous. And in this specific case, we're doing relative navigation, but also trying to determine the state and the principal axes of an unknown tumbling target. So this kind of simulates like an orbital debris removal mission or a servicing mission. And the goal of this is to estimate the state and then principal axes so we can do a nice motion plan that avoids collisions to rendezvous with the tumbling target, as you can see on the left there. And so looking at the frames for this problem, we have a chaser, we have a target, we have the camera frame, which is H there, and we're trying to determine the relative pose and velocity and angular velocity of the target, as well as the principal axis orientation. That G frame there is just an arbitrary coordinate frame based on the first point cloud that you get of the target, because you don't know anything about the target yet. You have to initialize something arbitrarily and then work that relationship between the true principal axes of the target. So the goals of our work, like I said, are to develop an on-orbit inspection framework using factor graphs and SLAM for relative navigation, and then pole hood analysis for the principal axes determination. And the big point of this work is to try to validate this on hardware on NASA's Aster-B free-flying robots, which are situated on the ISS, that are used for microgravity experiments. Like Courtney mentioned in her talk, it's a big purpose of our work is trying to figure out where these algorithms go wrong when you implement them on real hardware in a real microgravity environment. So just another quick thing on Aster-B. So this is developed by NASA over the past few years. They're the successors to the SPHERES microgravity research satellites, and their purpose is to assist astronauts and to test microgravity research. They have a lot of sensors on them. They run Ubuntu 16.04 and ROS as their software operating system. And for our work, we're really interested in using their IMU and the HAZCAM, they call it, which is a point cloud camera, time of flight camera. So some of our methods, so we're using factor graphs for relative navigation. So we get a bunch of front end measurements coming from the camera, the 3D camera and the IMU. So we can do chaser odometry between states at each time step using IMU. We can get target odometry of its rotation using point cloud odometry with using the time of flight camera. And then we also get range and bearing measurements to the target that help out. So these measurements go into this factor graph, connecting the unknown state variables via probabilistic factors. And then we perform incremental smoothing and mapping to solve for the best sort of collection of state variables that satisfy the factors. And so you can see an image of this. On the top is the green, which is the target pose chain at each step. And you're getting these point cloud odometry factors as it rotates, connecting the variables. And the bottom is the blue is the chaser pose chain, which you're connecting via IMU odometry. And then you're connecting them via these rotation kinematic constraints that allow you to resolve the full relative navigation problem. But that problem is still with respect to the arbitrary geometric frame, the G frame that I was talking about earlier with the target. And so we need to figure out the rotation between that arbitrary G frame and the true target's principal axes of rotation. And that can be done via what's called pole-hode analysis, where the target's pole-hode, which is the path of the angular velocity vector in angular velocity space, if it's represented in the principal axis frame, it'll produce central conic projections in each axis plane. So we can do an optimization problem to figure out the rotation that best aligns the omega vector to produce central conics, which you can kind of see in this image. We have in the middle that sort of noisy data of the pole-hode measurements we're getting and projecting that into each plane to create central conics, which for this tumbling body problem, you'll get 2 ellipses and 1 hyperbola. So some preliminary results in simulation. NASA has a really realistic gazebo-based ISS simulator. And so we were able to test this out with the target Aster-B simulating the motion of MVSAT, which is a large defunct satellite in low Earth orbit. And the chaser performed its inspection maneuver and did quite well in resolving its own navigational state, while also accurately estimating the target's rotational state in its principal axes. And so the timing of this conference is kind of interesting because we're in the middle of hardware testing right now on the ISS. So we performed one test just recently, and we're still kind of post-processing the data from that. And that first test was just to sort of run the algorithm, gather a bunch of data to try to now really tune it for a second test session, which should be happening in early July. And some initial takeaways from the hardware testing. So we had really good chaser state estimation. The IMU integration was actually working quite well, even though it was significantly noisy. But really the point cloud range and bearing measurements were doing well. Our pole-hode analysis wasn't quite working well in C++ yet. We had it working well in MATLAB for simulation analysis, but that's going to be a big improvement I think we expect to see in July. And just trying to improve the computational tractability of this. We can run it reasonably in real time on the hardware, but you got to watch out for bottlenecks in the point cloud registration steps for odometry. So yeah, that's all I have. If anybody has any questions later, find me at the poster session.
Presentation will be on spacecraft time series anomaly detection using transfer learning, and it will be given by Sriram Bayoredi.
Yeah. Okay, so yeah, hi everybody. My name is Sriram, and I'll be giving a brief presentation on spacecraft time series anomaly detection using transfer learning. Just like to quickly note that our research was sponsored by Lockheed Martin Space. So let's first touch on the motivation. So there are numerous spacecraft systems collecting vast amounts of data in space. And these systems need to be monitored for abnormalities that can function as precursors for system failure and or reboot, which is not like ideal, an ideal situation. Experts can monitor data channels and flag anomalies manually, but this can be time consuming. And when we're dealing with thousands of channels, it becomes a near impossible task. Machine learning algorithms have proven to be effective to do this in an automated fashion. But again, as we talk about scale and thousands of channels to monitor, training a channel specific model from scratch seems less effective. So in this paper, we basically propose using a trained general model that can quickly fine tune on specific channel data to obtain anomaly detection models that have reasonable performance. And then we also explore using knowledge of one spacecraft's data and systems to quickly learn information about another, which is useful depending on the amount of data available. So in most cases of time series anomaly detection, there is a lack of labeled anomalous data. Thus, the first step is usually in like the literature, the common successful approach is to train a predictor model that learns the normal behavior of time series. And then because predictor models can't be perfect, you can then model the prediction error you get on the training data and consider that as your expected prediction error. And then during inference, when you get the inference prediction error, you fit those errors to your probability model and threshold to find any unexpected errors based on their likelihood. In our experiments, we use two data sets. One is a subset of a Mars Reconnaissance Orbiter, or MRO data set that consists of 50 telemetry channels that reflect a broad range of the expected behavior in the channels. These were selected by experts from Lockheed Martin. And then we also use the publicly available SMAP MSL data set that consists of 81 total telemetry channels with labeled anomalies. In our experiments, we use the MRO subset to train our general predictor model, which we call MRO-net, and then we fine tune that model on channels from the SMAP and MSL data set. So here's a quick like overall diagram of our approach. The upper part here shows the training on the MRO data. So we get the MRO-net model from here, and then we fine tune on the SMAP MSL data. We use two strategies, one where we fine tune just the fully connected layers. So we call that MRO-net FC, and then the other one is where we fine tune everything, which we call MRO-net FT. After fine tuning, we obtain the prediction errors. We model the expected prediction, or we model the errors using kernel density estimation, and then use a dynamic thresholding algorithm from this paper here to identify the anomalous sequences. So here are recall and precision results for anomaly detection. The three models that I mentioned, MRO-net, and then the fine-tuned field connected and fully fine-tuned models, their performance is shown here. And then an identical model trained from scratch instead of pre-trained on MRO data is like the entry with LSTMs. And the performance, as you can see, when we go from the pre-trained model to fine-tuning, gets closer to the trained from scratch models. We're also comparing against some approaches from literature. The best performing model here is from the paper I previously mentioned, and that's a stack predictor approach using SVM and LSTMs. And you can see there's still a little bit of room for improvement. But the other aspect of our approach is to look at how long it takes to train. And so that best performing model takes around 430 seconds to achieve, like an average time of 430 seconds to achieve its performance. When we train our models from scratch, they take around 70 seconds, and the best performing fine-tuned model takes half that time and a tenth of the time of the best performing model. So to conclude, in this paper, we basically show that fine-tuning a pre-trained general predictor model can lead to comparable results for anomaly detection with reduced training times. And then we also show that it's feasible to use knowledge learned from one spacecraft system to quickly learn information about another spacecraft system. In the future, we plan to establish a dataset similarity metric to efficiently select pre-training and fine-tuning data to make the process more efficient, and also looking at transformers and intention because these capture more unseen patterns in the anomalous time series data. Yeah, thanks.
by Padmaja Jonalajeda. Please go ahead.
Hello, everyone. I hope everyone can see my presentation. My name is Padmaja, and today I'll be talking about our work in automated detection of bed junction morphologies that indicate signs of life. So there has been some consistent growth in astrobiological research, and with the recent efforts of the Perseverance rover, we identified the need for remote automated tools that can extract information from cross-sectional imaging data. And so for this research, we go back to our origins, which means we go and study the Ediacaran period, which has a very unique sedimentological record. As you can see in this figure, the structures here are called double ripple waveforms. And these double ripples are basically considered to be definitive signs of life. And this is because only in the Ediacaran conditions that consecutive storm events actually stack on top of each other, thereby preserving the organic mats and preserving the fossil structures. And this is special to the Ediacaran condition, and that's why it's considered to be a definitive biosignature. This actually helps us because the images here are cross-section images, and a lot of the images that we get from Mars or even a lot of extraction processes, we do get cross-sectional images. And so this would be really helpful in conducting translational astrobiological research. And so to develop such a tool, we propose our method called SpaceX, which is a scene-aware perception automation algorithm using composite embedding for segmentation. So one of the first problems that we noticed is that the data that we collected was from the excavations in Flinders region of Australia, which is massively unrestricted, which means we get a lot of issues such as variation in ripple thickness, variation in field of view, shadow artifacts, object artifacts, variation in daylight, atmospheric conditions, shadows, and a ton more issues, right? And the thing is, a lot of the practical imaging data that will be collected would actually have the same issues. And so the first thing that we noted was that whatever our model would actually be robust to these issues. And second thing was, as you can see in these figures from 1 to 5, there are a lot of ripple-like structures which are not biotic because they're not marked in green. There are a lot of artifacts and shadows which can be similar to ripples in the feature space, but they're not actually ripples. And so what we want is for SpaceX to detect perceptually meaningful ripples and reject the meaningless artifacts. And we believe that a combination of these two would help us do translational research. To that end, the scene-aware part of our algorithm is basically to make it robust to the practical imaging condition so that when it is parsing the scene, it should be aware of these issues. And secondly, to perform the perceptually meaningful detection, we have to automate that perception. And a combination of these two would actually give us translational algorithms. And to develop that, the SpaceX is actually made of two parts, which is Cora and SG. The reason we added Cora and not just developed a deep network and trained it is because our data is not only variable, but it is also limited. And so we wanted our model to actually be guided by something extremely deterministic and mathematically tractable. And so that algorithm looks something like this. What it does is it casts our image into a higher feature space and then develops a composite image, which is a higher level expression of the same image. And we perform energy contour and gradient optimization on this. The output is essentially region activation, meaning the image is telling us, oh, these are the region where the ripples will be present and everything else you should reject. And this is actually used as context or attention to guide the deep network. And that deep network is not just using an attention vector, but at various levels of abstraction, it is combining that activation, guiding the network, and then at every level of de-abstraction, essentially, it is doing a feature fusion. And we noted that this actually gives us a very, very stable and robust output. This can be seen in our results as well. I have a lot more comprehensive results in the paper for people who are interested. But looking at the top 3 algorithms and comparing it with SpaceX, we can see that SpaceX is extremely robust to oversegmentation. It is not confusing shadows to ripple artifacts. And when the field of view is changing highly in image C, it is not combining or smooshing together the ripples, which are very thin in nature. So we see that a lot of these issues are being tackled very effectively, and that gives us a really positive direction to build on, because the SpaceX is accurate. It is clearly able to do scene-aware detection and perceptual detection. And we know that the combination of deterministic region activation guiding a hierarchical level abstraction and feature fusion of a deep network gives extremely perceptually meaningful and robust output. I would be very happy to discuss the mathematical concept behind it, our energy function, our optimization function, and everything about the deep network and more comprehensive results in our poster. And I invite you all to please attend the poster. I would like to thank our collaborators as well, who collected the data from the Flinders region of Australia and the NASA exobiology grant from which we were funded. And thank you for giving me a chance to present my work.
And we will now be moving to the final presentation, which will be Visual SLAM for Asteroid Relative Navigation by Mary Gandor. Please go ahead.
Hi, everyone. I'm really excited to present my paper today. I hope you can all see my screen right now. So I'm a PhD student at Georgia Tech, and I work with Dr. Skinner, Travis Driver, and Dr. Siotris. I'm going to be talking to you about SLAM for asteroid relative navigation. And I guess I got lucky today because Courtney had a very nice presentation earlier today, explaining some more of these concepts in detail. But for us, relative navigation with asteroids is really important because it situates science data at the time of acquisition. It can inform safe and efficient path planning, control, and maneuvering. It can facilitate detailed mapping. These are really important aspects of an asteroid mission.
Megan, sorry if I interrupt. I don't think we see your screen, actually.
Oh, I'm sorry. Do you see it now?
Yes.
Okay,
Great,
sorry. I hadn't pressed on share. Okay, so yeah, I'm going to gloss over these details. I think Courtney has talked about these. So in the very recent missions, we've had a lot of more and more daring maneuvers that have been happening, mainly because of an increase in autonomous operations. OSIRIS-REx recently with TACSAM, which was really impressive. However, asteroid missions present their own challenges, as was explained earlier, where there's poor imagery of the target before arriving in situ, and poor knowledge of target characteristics. And this means that we don't really know what we're going to see once we get there. Debris and particle and harsh lighting can also deter most traditional ways of capturing features, image features from images around the asteroid. And long ground trip lifetime communication delays means that we can't really have a ground in the loop process that is very efficient. So because of this very heavy ground segment involvement, we're really interested in finding a way of increasing autonomy and to address these challenges and to maybe enable more possible mission designs and to reduce the costs. So based on these aspects, we're interested in doing relative navigation in a more autonomous fashion, as explained. And the idea is to do some kind of fusion, some kind of filtering of all kinds of data. So we have high frequency data, we have low frequency data, we have images. And what's great is that we have a framework to do this, and that's factor graphs and essentially graphs, inference graphs. And these can be the framework for inference and fusion in our work. And so what we did is that we implemented GTSAM and ISAM implementation C++. You can see the view down here, where we did a front end and a back end formulation, the front end doing description, detection of features, using orb features for the moment as placeholders. We can have robust features in the future. This is part of the work that we're doing. And the back end, essentially doing an incremental graph growth and smoothing. And the idea behind this is to be able to do this navigation precisely and autonomously. And so to validate our method, we used real imagery from NASA. And this is, I think, kind of the main contribution of our paper. We use this imagery from NASA's PDS archives, and we compared this against NASA's SPICE kernel values so that we can obtain a ground truth comparison. And so you can see here the result of this running. It might be a little choppy on the zoom view, but what you're seeing is the estimation of the camera pose and a landmark map being constructed underneath on the asteroid. And on the bottom right, you can see the image of the asteroid as it's rotating underneath the spacecraft. And this is essentially happening in real time here, but between each of these images, there's several hours in reality, if not more. And so we can get a very nice map of the asteroid. Here you can see there are blue and red dots. The red dots represent inliers, and blue are points that the algorithm excluded as outliers. And so based on this, we conclude that we can actually use this framework for relative navigation, and several improvements are still required. For example, we can incorporate motion and model dynamics and improve the landmark feature point management. And these are things that are being studied at the moment. I have other papers on this work. I've left many things out of the slide, so please come see my poster. I want to mention that our work was supported by a NASA Early Stage Innovations grant, and I'd love to talk to you at the poster session. On a side note, I would like to show you some cool stuff that we're doing here. We have a very nice platform for experimental setups at Georgia Tech. Dr. Siotros' Astros experimental setup, and we can generate now these really cool images and sequences of asteroids. We have a collimated light. We have cameras on board this our spacecraft simulator, and so we can generate these scenarios to test our algorithms even further. And so, yeah, please come see my poster. I'll be very happy to talk to
you. TJ, thank you to all the presenters, and TJ, over to you again.
Yep. So just a reminder of how to get to Gatherly. I'm trying to share my screen again. Maybe some of you are already there, but those of you who aren't yet, you'd go back to the landing page. Am I sharing the screen with the landing page? Probably not, sorry. I need to share the window. Here we go. Okay, so here's the link. Click on it. You need to set up your video and audio as per usual. And then once you get in there, it's like a whole conference floor. Navigate to our workshop. See you there. You should be able to keep your Zoom open as well at the same time. We've tried it before. Hopefully that doesn't crash.
TJ, what time should we come back to the call, to the Zoom call?
We'll make a floor announcement in Gatherly for everyone to come back.
All right, thank you.
Hello, this is TJ talking to everyone from the Zoom, not from Gatherly. So hope everyone's back here safe and sound. Let's see who's still here. Yep, okay. Is Bo still here? Yep, Bo's still recording. Perfect. So I will, let me type a message back to Luca quickly.
Okay.
Okay, so allow me to share screen again. Okay, the moment we've all been waiting for. Okay, so here are some statistics with the workshop. For the workshop, we had 32 paper submissions. Honestly, this is a great number. All the organizers were very happy with this. When we made a submission to the workshop program, this is apparently the first space-related workshop in CVPR for the past 10 years, probably. And so we weren't sure what sort of reception we're going to get. The fact that we got 32 submissions was a great outcome in our opinions. We had 33 kind, tireless, generous reviewers, experts as well, obviously in their field of study, which are all relevant to the workshop. Reviewing was double blind. Each paper received at least two reviews. You authors would know that. And decisions were made by meta reviewers. So there were no conflicts of interest at all. We made sure of that. And out of 32 submissions, 17 papers accepted. 8 were presented today earlier. Okay, so those were the statistics. Now we're here to present the Best Paper Finalist Award, Best Paper Award. These two awards are for the whole workshop, so Block A and Block B, so covering the 9 papers in Block B as well. And the third award presented today is the Best Presentation Award for Block A. Okay, so why do we do it that way? Obviously, because we need to see the presentations first before we decide. And when you were presenting in the spotlight as well as mainly spotlight as well, also in Gatherly, our organizing team went around and voted for the best presentation. Okay, so before the awards, sorry, we need to thank our sponsors. We should thank our sponsors again. So, and after that, let's go with the Best Paper Finalist Award first. And the Best Paper Finalist Award goes to AI for Mars, the data set for terrain-aware autonomous driving on Mars. So this might sound a surprise, but it's not a paper from this block, but it's in Block B. So if you're interested to find out about this paper, attend Block B tomorrow. Some of the reasons why the organizers, so basically the program chairs, thought that this was a great paper. The reviewers said this is the biggest data set released from another planet so far. Extensive explanation of the methodology and also the steps taken to get these high quality training data sets. And the demonstrable application of the results are clear. Autonomous driving on future Martian rovers. Congratulations to the team. First author, Michael Swan, and his colleagues as well. Thank you very much. So now for the Best Paper Award, it goes to Improving Astronomy Image Quality Through Real-Time Wavefront Estimation, presented today by David. Congratulations. to David and his colleagues from Stanford University and Lawrence Livermore National Labs. Why did we think, the program chairs think that this is an award-winning paper? The authors proposed a method for improving astronomy image quality using a neural network. So that describes what it's doing, but the reasons for valuing this work is that the solution is proven to be accurate and fast, which makes them potentially applicable in new telescopes. A very interesting and comprehensive study supported by well-designed experiments and sound results. To me personally, it's a very creative application of convolutional neural networks in an application that's really unique and interesting. Thank you very much for your contribution. Do we have David here? David, you still here?
Yes, I'm here. Thank you so much. This is an incredible award and has been an amazing conference. Yeah, I'm really humbled by this. Thank you.
Thank you. Okay, so I kind of revealed it by not going to presentation mode, but the best presentation award in Block A it goes to SpaceSec automated detection of bed junction morphologies indicating signs of life in Ediacaran period. And Padmaja presented the paper earlier today. I think the paper, we all thought that the paper was really, really inspiring. A unique application of machine learning techniques, well, computer vision techniques, as Padmaja mentioned earlier. Everything that most of the algorithms that she worked on needed to be deterministic and fast. So, but that's all good. We still count that as AI, but mostly she gave a really good account of what she's doing, and also the connections to discovering signs of life in other planets. Is an inspiring one. Congratulations. And thank you very much for your contribution.
Thank you so much. This is really exciting. Thank you, everyone.
Great. Thank you. And thank you all and see you again. Hope you enjoyed the Block A of the workshop so far. I broke up a few discussions earlier in the poster session. You are welcome to move into that room again to continue your very lively and active discussions. I don't think they will lock us out, so feel free to do that. We have Block A in a few hours' time. It's 2:15 a.m. in Adelaide here, so I'm heading to bed soon. But hopefully many of you will still be at Block B tomorrow. See you later.